So in this video we're going to solve a second order homogeneous linear differential equation with constant coefficients. How exciting is that? In the case where the characteristic polynomial has complex roots. So in the box down here I've summarized the solution process that we developed for the case where the characteristic polynomial had complex roots. Again, those complex roots are going to occur in conjugate pairs, alpha plus or minus beta I. We need the alpha and the beta to get our general solution. You look at the differential equation, you want to verify that it is a second order linear homogeneous differential equation with constant coefficients. In this case, it definitely has constant coefficients. They're all 1. And we use those to construct the characteristic polynomial. So it's going to be 1r squared plus 1r plus 1 needs to equal 0. And again, we can solve this for our roots any way that we wish. We can try factoring, although in this case factoring might not be the easiest thing to do. We can use the quadratic formula, although I would prefer that you don't. I would prefer that you practice completing the square. In this case, I'm going to complete the square on this. I'm going to subtract 1 from both sides, which is going to leave me r squared plus r on the left-hand side. In the completing the square process, you take half of the linear coefficient, so half of 1 is a half. And then you square it, so 1/2 squared is a quarter. You add that quarter to both sides. So -1 plus a quarter is going to be -4/4 plus a quarter is going to be a -3/4. And then we completed the square, so it's going to be the variable r plus whatever thing we squared. We squared a positive half. And now we take the square root of both sides. When we take the square root of both sides, we get a plus or minus the square root of -3/4. But we can simplify the square root of -3/4 because we can take the square root of the numerator over the square root of the denominator, and we recognize that -3 is the same as -1 times 3. And the square root of -1 is I, so we get square root of 3 times I over the square root of 4 is 2. So right here we really have plus or minus root 3/2 times I, and then we subtract 1/2 from both sides. We get r equals -1/2 plus or minus the square root of 3/2 times the imaginary unit I. And then our alpha is going to be the real component of this complex number, so alpha is going to equal -1/2. And beta is going to equal the real component of this complex number, which is the root 3/2. And then we just pop stuff into our formula template that we developed in video 4, I think, is when we developed this as a legitimate solution. So we wind up getting y equals, it's going to be e to the alpha x, so e to the -1/2 times x times c sub 1, one of our constants of integration, times the cosine of beta, but beta is root 3/2 from right here, times x plus a second constant of integration times the sine of the square root of 3/2 times x. And that's our general solution. Again, if we had initial conditions, we could look for the particular solution that went with those initial conditions by solving for c sub 1 and c sub 2. But I leave that to you as an exercise in the homework. Have fun.